Hey guys, today we will discuss about Bolzanos theorem of continuity. But first we have to learn neighborhood property of continuity. So let's start. Neighborhood property. If fx is continuous at x equal to a and fa not equal to 0, then there is a neighborhood of a where fx and fa keeps the same sign. So this is neighborhood property. Now we will go to Bolzanos theorem. Now let's see. Bolzanos theorem of continuity. So first see what is the statement of Bolzanos theorem. That is, if fx be continuous in AB, this is an interval, and FA, FB are of opposite sign, less than 0. If both are opposite sign, then obviously this is less than 0. Then there exists at least one value x in, it will be open interval AB, for which fx vanishes. Okay, this is the statement. Now we have to prove Bolzanos theorem. So first take a help of a graph. So this is x-axis and this is y-axis. Now let this is the graph of fx. Take this point as P, AFA, and this Q, BFB. Okay. Now first we have to just make the plot of this theorem from this graph. Then we will go to the main theorem. So here given that FA, FB less than 0. First take it. This is plot. Okay. Here FA into FB less than 0. This implies that FA and FB are of opposite sign. Okay. So if these are of opposite sign, then let's assume that f of a less than 0 and f of b greater than 0. So we have to prove that in this interval AB, obviously at least one point where fx is equal to 0. So first we will divide this interval into n subinterval. Okay, so the subintervals AB is divided into AX1, X1, X2, X2, X3, and in this way Xn minus 1 Xn. Now let at x is equal to xp plus 1, fx is greater than 0. Now if fx is greater than 0, now look at here, if let's choose that this interval we have taken xp plus xp plus 1. If this point is xp plus 1 and here f of xp plus 1 greater than 0, then obviously xp will be this one or this one. Okay, so we can say that f of xp is less than 0 or f of xp is equal to 0. Now if f of xp is equal to 0, then we get that at x is equal to xp, fx is 0. So in this case theorem is proved. Okay. But if not, if this case occurs, then what will we can say? Then obviously the interval xp plus 1 again will be divided into n subintervals. So xp plus 1 is divided into n subinterval. Now to prove this, we just rename this as a1 b1, and now this interval will be divided into n subinterval. Okay, so here length of a1 b1 will be b minus a by n. Okay, so now if we take that one of the subinterval is a2 b2, then here f of a2 will be less or equal to 0 and f of b2 will be greater than 0, such as, actually we just assume this. Now if f of a2 less or equal to 0, then f of a2 is equal to 0, theorem is proved. And if not, then again we will proceed in the same manner. We will divide this interval into n subinterval, then again we will take a3 b3, renaming obviously. Maybe we will get xm plus 1, where f of xm is equal to 0. Then we rename that this is a3 b3. Then proceeding in this way, we will get a sequence of interval just like this. And what will be the length of this interval is b minus a by n to the power k. Okay, because here if length of this interval we calculate, then what will we get? Length of this interval will be b2a2 b minus a by n square. Then we will get this. Now we can say that this ak b minus a by n to the power k tends to 0, as k tends to infinity. Okay. So in this way we can say that there is exactly one point where fx is equal to 0. Okay. And obviously we will get a point where fx vanishes. So we suppose that the point is alpha. So let that f of alpha equal to 0. That is, at x equal to alpha, fx is equal to 0. Now we have to prove that f of alpha equal to 0. Now if possible, let f of alpha not equal to 0. Now let this point is alpha. If f of alpha not equal to 0, then the curve will be continuous. Okay, so let's try this. F of alpha not equal to 0, then fx is continuous. Then the definition says that for given epsilon greater than 0, there exists a delta greater than 0 such that f of x minus f of alpha less than epsilon whenever mod of x minus alpha less than delta. So from this what we can say, x belongs to open interval alpha minus delta, alpha plus delta. We can say this. Now we go back to this point. Okay, let us choose that k is too much large. So choose k is so large. Okay, such that bk minus ak less than 2 delta, so that this interval ak comma bk subset of alpha minus delta, alpha plus delta. And as usual we can say that f of ak less than 0 and f of bk greater than 0. Just assume this. Okay. Now we will use the neighborhood property. What was that? If fx is continuous at x equal to a and fa not equal to 0, then in the neighborhood of a, fx and fa keep the same sign. So here we can say that in this interval alpha minus delta, alpha plus delta, in this interval we can say that fx maintains same sign for some delta. And also we have to let this also, f of a not equal to 0. Here a is equal to alpha not equal to 0. So if all fx maintain same sign, then obviously ak and bk maintains the same sign, and then we can say that f of ak and f of bk does not differ in sign. Unless, obviously we have to say this, unless f of alpha equal to 0. If f of alpha is equal to 0, then we can say this less than 0 and this greater than 0. But if f of alpha not equal to 0, then by neighborhood property we can say all fx as f of ak and f of bk maintains the same sign in this interval. Hence the theorem. So this was the plot. Okay, this one and this one. Now we will write from this plot our theorem. This is our theorem and this is the graph. So first we have to say that FA, FB less than 0, then FA, FB are of opposite sign. So let's write this. So if FA and FB are of opposite sign, then we can suppose, for definiteness, let us assume that FA less than 0 and FB greater than 0. Now let the interval AB x1, x1, x2, and in this way xn minus 1 xn. Okay. Now we supposed that as x is equal to xp plus 1, fx greater than 0. So let's write this. Be the first of these points at which fx is positive. And then we said that in the point xp, f of xp less than 0 is equal to 0. So let's write this. F of xp less than 0 or f of xp is equal to 0. If f of xp is equal to 0, then the theorem is proved. If not, that is f of xp less than 0, then the interval xp plus 1 again divided into n subinterval. So first rename this as a1 b1 Now we will divide this, and the length of this interval b minus a by n. Obviously this was the subinterval of AB, so it will be length of A1 B1. Now we divide A1 B1 into n equal subinterval and consider the sign of the function fx at the point of division. Okay, now we took that A2 B2 is the first interval where f of A2 less or equal to 0 and f of B2 greater than 0. So let's write this. Where f of A2 less or equal to 0 and f of B2 greater than 0. If f of A2 again equal to 0, then the theorem will be proved. If f of A2 is equal to 0, then and if not, then again we will divide this into n subinterval. So is, you can say this is, or B maybe. Interval, what was that? AK, BK, and the length was BK minus AK is equal to B minus A by n to the power k tends to 0 as k tends to infinity. In this case, we just consider that there will be x is equal to alpha where f of alpha equal to 0. So let's write this. This shows that exactly 1 point alpha, which is common to all the intervals we shall show that f of alpha equal to 0. Now we have to suppose that f of alpha not equal to 0. Then there will be contradiction. Then we can say that f of alpha equal to 0. Now let's move to that part. If f of alpha not equal to 0, then we discussed that fx is continuous, and then we will use the definition of continuity. Then by the definition of continuity, for given epsilon greater than 0, there exists a delta greater than 0 such that mod of fx minus f of alpha less than epsilon whenever mod of x minus alpha less than delta, that is x belongs to alpha minus delta, alpha plus delta. Now we said that we have to choose k so large that it will be less than 2 delta, and this interval will be the subset of this open interval alpha minus delta. So let's start this. So large so that alpha plus delta and f of ak less than 0, sorry, here this is 0, and f of bk greater than 0. Now we used the neighborhood property. So by neighborhood property, continuous function, obviously we have to mention because there is a neighborhood property of limit. So this will be fx maintains the same sign in a neighborhood of alpha minus delta, alpha plus delta for some delta when f of alpha not equal to 0. Hence f of ak and f of bk keeps the same sign, or this just cannot differ in sign. Unless f of alpha equal to 0, hence the theorem. So it was Bolzanos theorem, and this is, you can prove easily if the plot is clear for you. Then you can say, obviously you have to remember this neighborhood property, and then you can prove this Bolzanos theorem. Here we have to remember just this part, and we just proceed from this, and then we will get this x where fx vanishes. So today I end this lecture here. If this video is helpful for you, then please hit the like button and share this video with your friends. So goodbye.